Hi everyone. Today we're going to be talking a bit more about electric current. In particular, we're going to be looking at the motion of electrons as they cause an electric current. And of course, this motion is caused by fields and voltages. Now, if we don't have any voltage applied to a metal, then the electrons in the metal will be in constant random motion. They'll be bouncing around in every which direction. They won't be stationary. If the metal is not connected to a power supply, then the net movement of the electrons will be zero. For every electron that's randomly moving right, there'll be another electron randomly moving left. If we take all of the electrons as a whole, then any electron going in one direction will be balanced by an electron going in the other direction. So there'll be no net movement of charge and no current through the wire, even though the electrons inside it are moving around. So there is no net movement of charge and no net current as long as we don't apply a voltage across it. So what happens when we do apply a voltage across it? Do they all suddenly line up and start moving in one direction? Well, you might expect that, but the answer is in fact no. If a conductor is connected to a power supply, an electric field appears in the conductor. In this diagram, that's represented by an E, with an arrow showing the direction of the field. But you can see that the electrons are still bouncing around quite a bit. As the electrons move, though, they tend to slowly drift in one direction. That means that for every electron going in one direction, the electron going in the other doesn't quite manage to cancel it out. And so the net movement of electrons is slowly drifting in a particular direction. This is sometimes called the electron drift. And this is the electric current of the circuit, this slow meandering movement of electrons. The reason that electricity seems to travel so fast is not because each individual electron in the wire can travel across very quickly. It's because all of the electrons in the wire start moving at the same time. So you put a few electrons into one end of the wire and a few come out of the other end, but they aren't the same electrons. It's like a wave has been carried forward to the end of the wire. The actual speed of the electrons through the wire is only about walking pace. It's not very quick, but the reason electricity carries so much power is because there are so many electrons in each part of the wire. Now, the electric field that we use to move the electrons is created by a power supply. A power supply in the lab might look something like this photograph. If the power supply produces a potential of W in a charge Q, its voltage is V equals W over Q. Sometimes we use E for energy, but this time we're going to use W for energy. Otherwise, we might get it confused with electric field. So if a particle gains potential energy of W and its charge is Q, this is how we find what voltage it's being exposed to. Of course, this works the other way as well. The potential energy of a particle when it's exposed to a voltage is W equals V times Q. So the potential is used up as the charge passes through the circuit components, right? When it passes through the circuit components, it sort of rolls down the hill of potential. It loses potential energy, and the potential energy is radiated away as heat from the circuit component. So when current flows through a circuit component, we say that the potential drops. The potential will go down because the particle is losing potential energy as it passes through the circuit component. But if we have the potential dropping, that means that there's a potential difference between each end of the circuit component. So if we have a charge Q passing through the circuit component and it loses a potential energy of W, then the voltage drop across the wire is given by V equals W over Q, which is the same equation as we saw on the last slide. The potential is used up because the circuit components cause the electrons to lose energy. So they have potential energy, and as they roll down the potential hill, as they pass through the circuit component, they lose the potential energy. And any kinetic energy that they would have gained is instead transferred to the circuit component, which can cause it to glow if it's a light bulb, or get hot if it's a resistor. Now in physics, we assume that the wires that the charged particles pass through are almost perfect conductors. This means that they don't cause the electrons to lose energy as the electrons flow through them. So the voltage drop across wires is very close to zero. Remember that the voltage drop is proportional to the amount of energy they cause the electrons to lose. So if the wires don't cause electrons to lose energy, then there's no voltage drop between them. And if you were to connect a voltmeter to just an empty wire, you would get a reading of 0, or very close to 0. So that's the end of the theory. We've learned about the motion of electrons as they pass through a wire. Let's go on to some questions.